Hello and welcome to our video. In this lab project we will explain in detail how we perform practical exercise 5. Electromyography or EMG measures muscle response or electrical activity in response to a nerve's stimulation of the muscle. EMG is, for example, used to help detect neuromuscular abnormalities. EMG measures the electrical activity of a muscle during rest, slight contraction, and forceful contraction. Muscle tissue does not normally produce electrical signals during rest. An EMG signal is based on the simple fact that whenever a muscle contracts, a burst of electric activity is generated which propagates through adjacent tissue and bone and can be recorded from neighboring skin areas. Internally, when contracting, muscles produce voltages of around 100 mV. However, because there's a lot of tissue between the muscle and the electrode, the signal weakens a great deal before it reaches the electrodes. Therefore, it is really important to amplify these signals using amplifiers. The pictures to the right shows an action potential of magnitude 100 mV and a picture of an EMG signal waveform. EMG activity is linearly related to the amount of muscle contraction as well as the number of contracted muscle fibers, or in other words, the stronger the muscle contraction and the higher the number of activated muscle fibers, the higher the recorded voltage amplitude will be. EMG signals contain frequencies ranging from 10 Hz or lower up to 1 kHz or higher. Our goal in this exercise was to light up a diode when we contracted our muscles. Here are the parts that we used for this experiment. In the next few slides, we will explain what each part does to eventually light up the LED. An instrumentation amplifier allows an engineer to adjust the gain of an amplifier circuit without having to change more than one resistor value. An instrumentation amplifier is a differential op-amp circuit providing high input impedances with ease of gain adjustment through the variation of a single resistor. Looking at the photo on the lower right corner, V1 and V2 are connected to the muscle that is being measured, and Vout is the output from the amplifier, which will then be connected to the second order bandpass. Next, we chose a gain resistor, RG, such that the total gain of the amplifier was approximately 10 because we didn't want to amplify the noise too much. The equation for the gain is derived from the two central 25 kΩ resistors connected to the gain resistor downstream and can be seen in the upper right corner. Here are our calculations for the resistance gain in the instrumentation amplifier. Here you can see our setup for the circuit and how we connected our instrumentation amplifier. Next, we assembled a second order bandpass by combining a second order high pass and low pass filter with our amplifier. The resistors and capacitors were equal within both filters since we still didn't want to amplify any noise. The ideal range for EMG is 10 to 500 Hz, but we wanted to avoid 50 Hz artifacts from electronics in the room, so we used the frequency 100 to 500 Hz. We used the equation in the top right corner to calculate the second order high and low pass cutoff frequency. A filter is a circuit capable of passing or amplifying certain frequencies while attenuating other frequencies. Thus, a filter can extract important frequencies from signals that also contain undesirable or irrelevant frequencies. High-pass filter cancels out frequencies below a certain frequency, and low-pass filter cancel out frequencies above a certain frequency. Second-order filters are an important type of active filter design because higher-order filter circuits can be designed using them. They are sometimes referred to as VCVS filters because the op-amp is used as a voltage-controlled voltage source amplifier. Using a second-order filter is recommended in our case as they provided a roll-off of 40 dB per dS as compared to 20 dB per dS provided by first-order filters. In these filters, the use of active components will separate the filter from the rest of the circuitry. Therefore, due to the greater amount of noise inherent in unfiltered EMG, we wanted to build these filters without any gain. After filtration, we designed a non-inverting amplification circuit that amplified the desired signal from the ENG, which I will be talking about in a minute. Here you can see our calculations for the capacitors and resistors in the high-pass and low-pass filters. Here you can see how we assembled our circuit with the filters. Lastly, we connected the output of the low-pass filter to a third, non-inverting input of the amplifier, as you can see in the picture to the right. The output of that amplifier was then connected to the LED. A non-inverting amplifier is an op-amp circuit configuration which produces an amplified output signal. This output signal of non-inverting op-amp is in phase with the input signal applied. In other words, a non-inverting amplifier behaves like a voltage follower circuit. A non-inverting amplifier also uses negative feedback connection, but instead of feeding the entire output signal to the input, only a part of the output signal voltage is fed back as input to the inverting input terminal of the op-amp. It is the value of the two resistors, RF and RG, that govern the gain of the operational amplifier circuit as they determine the level of feedback. We wanted a gain of 500, so we used the equation to the right to calculate the value of the resistors. In an EMG, we have both positive and negative EMG components. The circuit works correctly when the positive part of our EMG activates and the LED turns on. An EMG circuit on a breadboard does, unfortunately, have its flaws. When one of our group members tested our EMG, it seemed so that the negative component of the EMG was turning on the LED. That is, the function of our circuit was exactly opposite to how we wanted it. Then, when another person tested out our EMG, it worked perfectly and correctly. It is quite clear that the EMG circuit is subjective. That is, it varies depending on the individual testing the EMG. When the LED is constantly on, the gain is too much, which means we're amplifying the noise as well as the EMG signal. We want to isolate the EMG signal, so we have to lower the gain so it doesn't amplify the noise as much. When the LED is constantly off, the gain is too low and the amplifier doesn't amplify the signal from the EMG enough, or over 5 watts. Here you can see our base calculations for the resistors in the non-inverting amplifier. It turned out that this gain did not work for our circuit, so we had to try different resistance gains. These are our final resistor values after testing the circuit a few times. Here is Esther testing out our circuit. The EMG worked opposite to how we wanted it for Esther, so we tried switching the LED. That is, instead of having it connected to ground, we connected it to the VCC and then we got the correct function. Here we have Halldór testing out our circuit and it works correctly for him. Here is Guðbjörg testing out our EMG circuit on her tricep. We needed a much higher gain for the tricep than the bicep.